So the next concept that we're going to cover is drug efficacy. And drug efficacy, again, is taken from the dose response curve. Again, this is a semi-log curve with percent max effect here. And if I redraw some drug curves, so this is drug A, and this is drug B. Previously, when we talked about potency, we took it from the 50% activity. Drug efficacy is actually a measure of the activity of the drug at 100%. So drug efficacy is a value that's taken off of what is the estimated 100%. So in this case, both drug A and B produce 100%, or they come to an asymptote of 100, drug efficacy. So A is the concept here is that drug A and drug B have equal efficacy. So they're equally efficacious. If we draw another drug here, and this is the effect of drug C, you can tell here that C, no matter how much drug you add increasing concentration, the max effect that you get from drug C will never approach 100%. It tops out, let's say around this is 60%. So drug C is less efficacious compared to both drug A and B. If we revisit the concept of potency now, again, potency is taken off of the EC50, but it's the EC50 of that particular drug's 100%. So drug A's potency would be here, B's potency would be here, and drug C's potency would be here. So this is approximately 50% of the drug C maximal effect. And when we take a look at these 3 points, drug A is the most potent, followed by B, followed by C. C is a drug that can be described as having lower efficacy and lower potency compared to drugs A and B. So the next concept that we're going to cover are receptor activation curves, particularly agonists and antagonists. So again, if we go back to our dose response, and this is log drug, and this is percent max effect. If we are talking about agonists and antagonists, this can be a bit more specific. So something related to the receptor, for example, receptor activation. So percent receptor activation. So an agonist is something that causes the receptor to be activated. And again, here is drug A. It causes 100% maximum effect, 100% receptor activation. And this is called a full agonist. A full agonist is any drug that produces 100% or maximum receptor activation. In contrast to full agonists, partial agonists, this is a partial agonist, produces less than maximum effect. And it can be anywhere less than a maximum effect. So the partial agonist can come up to here and come up to here, or be around 50%. Full agonist refers to drugs that produce maximum or full receptor activation. Partial agonists, any drugs that produce less than maximum activation. So what does an antagonist look like? Well, you won't actually see the effect of an antagonist because it doesn't actually do anything to the receptor. So if you apply an antagonist to a receptor, there actually is no effect that happens. And this is in contrast to another concept of an inverse agonist. So an inverse agonist differs from a partial agonist and full agonist is that it causes the opposite effect. It also differs from an antagonist because it actually does cause an effect. So as an example, if this receptor was a GPCR that was linked to intracellular cyclic AMP, the full agonist would produce 100% maximum increase in cyclic AMP. The partial agonist would also produce an increase in cyclic AMP, but it would be less than the max. The antagonist wouldn't do anything, and the inverse agonist would actually decrease cyclic AMP. So those are examples of agonists and antagonists. The last concept that we'll cover are types of antagonism. So previously I mentioned that if you have your dose response curve, and let's just call this maximum receptor activation, that you wouldn't actually see the effect of an antagonist on your receptor. So you can identify the type of antagonist by the way that the agonist curve reacts to the antagonist. And so there are two major categories of antagonists: competitive and non-competitive. So a competitive antagonist is something that competes with the agonist at the same ligand binding spot. So if I just say that this is your receptor and this is your ligand or agonist, your antagonist would come along and compete for that exact same spot. So if it is sitting here, your antagonist is sitting at that spot, if you have increasing concentrations of agonist floating around, it can eventually outcompete that antagonist. So that's why this is called competitive. And the way that a competitive antagonist looks, so this is your agonist without antagonist. If you now add increasing concentrations of your antagonist, your curve, your agonist curve, will look like this. So it will be right shifted. It will still produce the same maximum effect. You just need more of your agonist. And that's because when you add more of your agonist, you will compete off the antagonist, and the agonist will still be able to produce max effect intracellularly. So you get right-shifted curves. The more antagonists you add, the more agonists that you need to outcompete that antagonist. So that's a competitive antagonist. What is a non-competitive antagonist? Well, simply put, it's an antagonist that doesn't compete for the agonist binding spot. So now, I'll just redraw this. Okay. So for a non-competitive antagonist, there are several kinds. The first one we're going to talk about is irreversible. So on your receptor, your antagonist occupies the same agonist binding site, but this time it produces either a covalent bond, so an irreversible antagonist, or it has such high affinity for this ligand binding pocket that agonists are essentially unable to outcompete. So it doesn't matter how much agonist you have around it, it will not be able to kick off the antagonist. So how does this look? So this is your agonist without antagonist. And as you add increasing concentrations of antagonist, your agonist curve will look like this. So there's a drop in efficacy with increasing concentrations, because the more that you add, the more receptors are occupied, and the more the agonist can't do what it's going to do, and essentially, eventually it will have no effect if the antagonist is in high enough concentration to occupy a lot of the receptors. So that's the first type of non-competitive antagonist. The second type of non-competitive antagonist is not irreversible, but let's say your receptor is here, your ligand binds to its usual agonist binding spot, but now your antagonist binds somewhere else. So we call this other binding site an allosteric binding site. So there are subtle differences between the agonist curves in these two situations, and I'll just draw it right below. So again, here's your agonist. But with an allosteric binding site, or you can call this a negative allosteric modulator, you still get a drop in efficacy, but with increasing concentrations of your antagonist, it will be saturated. So you won't actually be able to drop the curve anymore. And that's because at this point, the allosteric binding site is fully saturated by the antagonist, and this is whatever equilibrium exists between the agonist in the situation and your negative allosteric modulator will end up being achieved when the curves come together. So this would be the maximum antagonism with this allosteric modulator.